Hello everyone, myself Muskan Patel from 5th Sem Bhaskara. Today's topic of my presentation is characterizing schedules based on serializability transaction support in SQL. So let's see the introduction to scheduling and transaction support. In the realm of database, scheduling and transaction supports are crucial concepts. Scheduling involves the organization and the management of concurrent transactions, ensuring data consistency and integrity. Concurrent execution of transactions is fundamental for maximizing support, throughput, and the resource utilization. On the other hand, transaction support encompasses the mechanism and the feature provided by the database management system to ensure the asset properties of transaction, atomicity and consistency, isolation and the durability. Let's delve deeper into the intricacies of scheduling and transaction support in database system. So let's see serializability definition. Serializability is a concept in database management that ensures that the execution of current transaction maintains consistency equivalent to the serial execution. Concurrent control, it allows multiple transactions to run concurrently while preserving the consistency of the database state. Isolation levels. The database system provides various isolation levels to control the degree to which the operation of one transaction can affect or to be affected by the other. Now let's see the techniques for characterizing schedules based on serializability. Precedence graph, equivalence classes, serializability theory. The precedence graph is a visualization tool used to represent the serializability of a schedule and identify the presence of cycles. Equivalence classes. The transactions are grouped into equivalent classes based on their conflicting operation, simplifying the analysis of schedules. Serializability theory. The mathematical theories and the algorithm are employed to ascertain the serializability of schedules and ensures the data consistency. Conflict serializability. The definition is it focuses on the ability to transfer a non-serializable schedule into a serializable one by resolving conflict among conflicting operations. Conflict operations. Operation within transaction that contain for the some data item resulting in potential inconsistencies if executed concurrently. Dependency graph. Dependency graphs are utilized to analyze conflicts and identify the serializability of schedules through graph-based representation. Use serializability, multi-vision, concurrency control, snapshot isolation, consistency maintenance. The multi-vision concurrency control views serializability in closely linked to multi-version concurrency control, which enables the concurrent execution of the transaction that reads and writes multiple versions of data. Snapshot isolation. The database implements snapshot isolation to provide each transaction with a constant snapshot of the database, ensuring view serializability. Consistency maintenance. The view serializability model maintains consistency by allowing transactions to predict according to the certain constraint, providing a constant view of the data. Now let's see the difference between the serializable schedules and non-serializable schedules. The serializable schedules guarantee isolation and consistency, ensuring that transaction can be executed in parallel while preserving correctness. Whereas in non-serializable schedules may introduce inconsistency, and an error due to the interleaved execution of transaction, potentially violating the ACID properties. The transaction support in database. The ACID properties, the database system ensure the atomicity, consistency, isolation, and durability of the transaction to maintain data integrity and reliability. Concurrency control. The concurrency control mechanism prevents interference between transactions, ensuring that the database remains consistent during concurrent execution. Recovery management. The transaction logs and the recovery protocols are implemented to recover the database to consistent state and in the event of failure or the system crash. Transaction support in SQL2. A single SQL system is always considered to be atomic. Either the system completes execution without error or it fails and leaves the database unchanged. With SQL, there is an explicit begin transaction statement. Transaction initialization is done implicitly when particular SQL systems are encountered. Every transaction must have an explicit end system statement, which is either a commit or a rollback. Characteristics specified by a set of transaction statements in SQL2. Access mode, read only or a read write. The default is read write unless the isolation level of read uncommits is specified, in which case read only is assumed. Diagnostic size n specifies an integer value n, indicating the number of conditions that can be held simultaneously in the diagnostic area. Isolation level. Isolation where isolation can be read uncommented, read commented, repeatable read, or a serializable. The default is serializable. With serializable, the interleaved execution of the transaction will adhere to our notation of serializability. However, if any transaction executes at a low level, then the serializability may be violated. The conclusion and the key takeaways are optimizing performance, data consistency, and robustness. The optimizing performance, efficient scheduling, and the strong transaction support are crucial for optimizing database performance and ensuring scalability under high loads. Data consistency, the characterizing schedules based on serializability ensures data consistency and integrity, crucial for reliable and accurate information for retrieval. The reverse transaction supports mechanism fortify database against failure and the data corruption, enhancing system stability. Thank you for watching my video.